Okay, let's dive right into this. Today, we are exploring a massive, truly fascinating breakthrough in the field of pediatric neurology. We're looking at a brand new framework for understanding exactly how a child's brain develops, how the networks inside it mature, and incredibly, how all of this can be measured while they sleep. It's a completely fresh way of looking at brain data, and honestly, it's going to change how we think about cognitive growth forever.
For decades, tracking the precise day-by-day development of a growing brain has been this incredibly complex puzzle for scientists. But ask yourself this: what if a child's sleep could reveal exactly how their brain is maturing? Because it turns out, by utilizing that unique, quiet, interference-free window of sleep, we are finally unlocking the secrets of the maturing brain in ways we literally never thought possible.
To really grasp how this works, we need to understand the core concept right here: timing architecture. So, the absolutely crucial point is that in this framework, we aren't just looking at the static, physical structure of the brain. No, we're looking at the actual rhythm, the dynamic temporal organization. Think of it like the highly precise millisecond by millisecond timing of how entirely different, large-scale neural networks across the brain communicate. It's how they integrate with one another to form coherent thoughts and actions. And to map out this wildly complex timing architecture, researchers have turned to the NCH Sleep Databank. Now, this isn't just some small sample size. This is an unprecedented repository of pediatric sleep recordings, all paired with longitudinal clinical information. I really want to emphasize the sheer massive scale of this dataset. Having thousands upon thousands of hours of data, it makes it an absolute treasure trove for discovering the hidden benchmarks of healthy developmental progress. Section 1. Sleep. The brain's window, watching networks reorganize in the dark. It is so easy to think of sleep as just, turning off the lights, but it's actually a period of intense neural coordination. The brain is incredibly busy working. As a child grows up, their brain undergoes some profound physical upgrades. We see myelination, which is essentially the brain wrapping its biological wires in insulation so signals can travel way faster. We see synaptic refinement, kind of pruning away the connections we just don't need, and massive overall network reorganization. These physical, structural, and functional changes are exactly what lead to increasingly rapid and efficient communication among distributed neural systems as that child gets older. And this brilliantly illustrates exactly why researchers are focusing on nighttime data. As this quote from the research highlights, sleep isn't just some byproduct. It plays a critical role in driving these developmental processes. Without the waking distractions of talking, moving, and processing the outside world, sleep serves as the absolute perfect laboratory for scientists to observe these network upgrades happening in real time. Section 2. Introducing the NeuroByte, a paradigm shift in brain analysis.
We are looking at a fundamental before and after moment in how researchers analyze brainwave data, specifically through the ECFJ framework, which is the developmental model driving this new research. Let's contrast these two approaches. Think of the human brain like a massive symphony orchestra. On one side, you have traditional EEG studies. For a long time, these focused on things like oscillatory activity, sleep stages, and spectral characteristics. In our orchestra analogy, that's kind of like measuring the overall volume and pitch of the music. But look at the ECEBJ framework on the other side. This new approach focuses on the dynamic timing architecture. It listens to the rhythm, the precise synchronization, and the exact timing of the different sections of the orchestra, the neural networks, talking to each other.
And the absolute star of this new framework is the definition right here: the NeuroByte. A NeuroByte is a transient integration event. In simpler terms, it's a distinct, measurable moment of coordinated large-scale neural communication. You can think of a NeuroByte as the fundamental unit, the building block of how a maturing brain organizes its thoughts in data. It is literally a spark of total brain synchronization. Section 3. Finding the signal, the detection pipeline. Now, you might be wondering, how do we actually find these NeuroBytes in hours and hours of squiggly lines? Well, here is the exact pipeline used to filter out the noise and find that signal. First, researchers use bandpass filtering to isolate specific frequencies, targeting precise regions on the scalp. We're talking about standardized coordinates known as F3, F4, C3, C4, O1, and O2. Step 2, they apply a mathematical tool called a Hilbert transform to extract the shape, or the amplitude envelope of the signal. In step 3, they normalize that data using z-scores just to make sure everything is perfectly comparable. And finally, step 4, event detection. That's where they find the spark. But how big does that spark actually have to be? A A candidate NeuroByte event is only officially flagged when that normalized amplitude envelope exceeds 1.8 standard deviations above the baseline. That very specific mathematical threshold ensures that what we're seeing is a true moment of large-scale coordination, cutting right through the normal background static of the sleeping brain. And here is the truly mind-blowing part about these integration events. They happen in the literal blink of an eye. Seriously, for an event to be recorded as a NeuroByte, it only lasts for durations between 30 and 500 milliseconds. That is incredibly fast. We are measuring the fleeting, tiny fractions of a second where the brain perfectly syncs up.
Now, what's really interesting here are the specific temporal features we extract once we actually find these events. We look at neurobyte density, which is how many sparks per minute. We look at the mean duration, but pay close attention to that third metric, mean IEI, or inter-event interval. We are actively quantifying the silent spaces between the events just as much as the events themselves. By measuring those intervals and the stability index, we can see exactly how consistent the brain's rhythm really is.
Section 4. The maturing brain from variability to stability. Okay, we've spent a lot of time in the milliseconds and the microdata. So let's zoom back out to see how this plays out over years of a child's life. I love this timeline because it guides us perfectly through the conceptual developmental trajectory of a human. In early childhood, the brain's rhythm is characterized by high timing variability. It's developing that network coordination, but it's a bit chaotic. Sparks are firing inconsistently. Then we reach intermediate stability. And finally, by adolescence, we see a mature timing architecture. The brain has organized itself. It's now capable of highly efficient, super reliable, large-scale integration. We can summarize the hypothesized developmental trends from the ECPJ framework beautifully right here. As a healthy, growing brain matures, neurobyte stability goes way up. Temporal variability goes down. The inter-event intervals become highly consistent, almost like a well-kept metronome. And integration timing becomes vastly more efficient. The brain physically becomes a much more stable and precise machine. Let's move along and see exactly how this builds step by step within the ECPJ model. It is a perfect cascade. Step 1, structural growth, like that myelination we talked about earlier, leads to improved conduction timing. Step 2, that speed leads to enhanced synchronization across the whole brain. Step 3, synchronization allows for stable neurobyte generation. Step 4, those stable sparks allow for efficient integration of information. And finally, Step 5, that efficiency results in true cognitive maturation. So, the physical, structural growth dictates the rhythm, which directly dictates how well the child learns and thinks.
Section 5. Future of Brain Health, Clinical Implications and Beyond.
This right here is the crucial what's in it for the kids part of the data. Because within this framework, neurological dysfunction is essentially a disruption in temporal organization. If a child's brain is struggling, it's going to manifest in the data. We might see reduced neurobyte density, wildly increased variability in the intervals between sparks, reduced timing stability, or just an overall delayed maturation of their timing architecture compared to their peers. The stakes here literally cannot be overstated. By finding these timing disruptions early through totally non-invasive sleep data, we could completely revolutionize the diagnosis and understanding of major conditions. We're looking at massive potential clinical investigations into pediatric sleep disorders, ADHD, complex neurodevelopmental disorders, and early cognitive developmental delays. It gives doctors a completely new, incredibly powerful lens to see the problem. And this brings us to the ultimate goal. This right here is exactly why the NCH Sleep Databank's immense, massive scale is so vital. With all that data, researchers can finally establish normative developmental timing benchmarks. They can build the definitive gold standard baseline for what a normal brain timing trajectory looks like at age 3, age 7, age 15. And with that baseline, we can accurately compare and actually help clinical populations.
To wrap up this explainer, I really want to leave you with this provocative thought. If neurological dysfunction is fundamentally a disruption in temporal organization, if it's an issue with the rhythm and timing of the brain, can we one day learn to rewrite the rhythm of the developing brain? It's a question that represents a complete paradigm shift, and it leaves the door wide open for the future of pediatric neurology. Thank you so much for joining me. Keep asking questions, and I hope this inspired you to look at the sleeping brain in a whole new light.